With this lecture, we are starting the engineering analysis of soils, and we are going to start that from stresses in the soil. So, what is stress? Stress is, as you know, as you should know from high school physics, force per unit area. So, and we are going to show stress, normal stress with a sigma in this course. So, yeah, that is valid and true for uh, homogeneous and continuous materials, but soil isn't like that. Soil has different phases. It has discrete grains, pores, etc. So this, yeah, worked to some extent, but people needed something more to model the behavior of soils. So for that purpose, uh, what people came up with, what the who is viewed uh, as father of soil mechanics, Carl Terzaghi, came up with is this. And by the way, a little interesting bit of trivia. He was working in Istanbul in Turkey in the early 20s, so you can consider soil mechanics was kind of born in Turkey. So he considers the stress, the total stress in the soil, is has two components. It has a, a stress component carried by the grains and the rest carried by the pore fluids. Actually, he didn't say that. He didn't write it that way exactly. What he wrote, or what he postulated, was this, where this first term, the sigma prime, is the stress carried by the grains, and he called that the effective stress. So it is the stress carried by the grain matrix or solid skeleton. And this is the pore pressure. And he separated that into water if saturated, air pressure, which is zero if dry. So actually, let's write it this way. So here, let's put a quick side note, quick parenthesis. When we say pressure of air, of course, you know that pressure of air is atmospheric pressure, which is like around 100 kilopascals. But for engineering calculations, so that's for scientific calculations. If you are going to use ideal gas law, you need to consider air pressure to be 1 atmosphere. But for engineering calculations, for mechanical calculations, you can use gauge pressures as well, because so gauge pressure shifts all pressures by 1 atmosphere, such that atmospheric pressure is 0. So the purpose of this is because when we are analyzing something for conditions where the air pressure isn't going to change, and for many engineering, many civil engineering projects, that usually is the case, then there is no point in adding one atmosphere to everything. So you have one atmosphere inside the tank, one atmosphere outside the tank. They are going to cancel anyway. All those atmospheric pressures are going to always cancel. So for that purpose, we use gauge pressures instead of absolute pressures. Absolute pressure is what you learn in science. Let's say 0 is total vacuum. So shift all absolute pressures by one atmosphere. So anyway, that is why if you have dry soil, the pore pressure is 0, because yeah, it is one atmosphere, but it acts on all grains from all sides equally. Therefore, it is going to cancel for every grain. So what about effective stress though? Effective stress is it has the solid skeletons contact stresses involved. It has a double layer repulsion. So even if, remember, we talked when we were talking about clay particles ability for holding water, we talked about these double layer cushions of water, and we said these cushions can transmit stress from grain to grain without the grains touching each other. So that's what this is. If two double layers are pressed against each other, they are going to be able to carry this stress without the solids touching each other. And then when you go down to clay scale, this even becomes significant. Of course, these two are valid for, or let's not say valid, significant for clay only. But anyway, in the end, the overall summary, the overall meaning of this is that it is the stress carried between the grains. So basically, it is something like this. So you have these grains for a granular soil. You can think of it as such. You can consider over this area, you are going to have your fluid forces, and imagine contacts are infinitely small, so they occupy almost no area there. And then you also have these contact forces. So you can consider the total stress carried by the soil is going to be the stress acting on the entire soil area. And as you can see from this figure, the uh, the pore pressure, the pore water, or actually air as well, also apply or also acts on the entire soil area. So the way the effective stress is defined is it's also defined over the entire soil area. So it is not the stress inside the solid of the grain. It's not the stress at the contact. It's not like that. It is kind of like the resultant of all these contact forces divided by the entire soil area. So it is like average stress. That's how you can superpose stresses. They have to be acting over the same area to make this superposition. So uh, keep that distinction in mind. It is not the stress in the solid. It is more like a conceptual stress that is a component of the total stress in the soil. So that's why it's called effective stress. So how do we calculate it then? Now uh, let's consider a column of soil like this. So here is my column of soil. And let's also put some dimensions here. Let's have it this much deep, and let's have it with an area of A, and let's have it with this much unit weight. And also let me do this so that it looks like a rectangular prism. Okay. So let's say we would like to calculate or figure out the stresses at the bottom, the vertical stresses. So the weight of this soil is carried by the vertical stress. So I can write directly that vertical stress is weight over area. And here for this particular figure, by the way, I'm going to be writing many equations in here, but they aren't formulas or anything. They will be specific to what I draw. So the weight of this is volume, Z times A times unit weight, divided by area A. Look what happened. It becomes Z times gamma. So wait a minute. The total vertical stress is calculated similar to hydrostatic pressures of a fluid. That's interesting. So you can pretend the soil was a liquid with that same density, and then your vertical stress calculations would still be the same. Now, let me add a level of complication to this. Let's add groundwater to this picture. This icon, this mark, designates the level of the groundwater inside the soil. And let's have it at a depth of, or at a height of ZW. Actually, we are talking in terms of depth, so let's call this ZW, so this would be Z minus ZW. So let's look at this again. Now, what have changed is, first of all, we changed the unit weight down here. Now the unit weight down here is gamma saturated. So my total stress becomes sum of all weights divided by unit area. So the area is always the same. So the area will always cancel out. So what we have now is this. Okay. And how much is the pore pressure down here? Now we are at this depth from the water surface. Now, yeah, there is soil inside that as well, but the soil grains there, they are just shaping the pores for your fluid. So actually it is just like a very intricate container in which you have water. So your water pressure will also be this depth times density. So it will be Z minus ZW times gamma water, which makes your effective stress, vertical effective stress, which is, as Terzaghi says, this much. And if you subtract from that, if you subtract this, you end up with ZW gamma bulk plus Z minus ZW gamma submerged. So that's called gamma submerged here. So let's see what we have done here. We have said, and actually let's add one more little detail here. Imagine if you had some additional load on the top, what would that do? It would just increase the total stress. So So the vertical total stress is weight of everything above, and with everything, we mean both soils and loads. U, as we already said, 0 for dry, hydrostatic for saturated. But let's put a note here. I said hydrostatic. What does that mean? Hydro, water, static, stationary. If the water is stationary, unless there is flow. So I'm going to leave it at that right now. So we haven't covered the flow chapter yet. Once we cover the flow chapter, we are going to go into that as well. But right now, until then, we are going to be looking at only hydrostatic groundwater problems in this section. And the effective stress is always this. Why is it so? Because it is defined as such. Because remember, effective stress isn't some real stress that you can measure somewhere. Its definition is this. So it always, this concept, is called Terzaghi's effective stress principle. So this never changes unless in some cases it does. But anyway, for this course, this is going to be the case. When does it change? If you have noticed, I always kept writing for pore pressure, 0 for dry, hydrostatic for saturated. But what if it is something in between? Well, if it is something in between, this doesn't hold anymore. So if it is a partially saturated soil, unless the soil is partially saturated. So if it is a partially saturated soil, this also ends up being something in between. So it is going to be a fraction of the pore pressure, but if it's partially saturated soil, the pore pressures will be negative due to capillarity. We are going to cover that later. So let me not get ahead of myself here. So the way we use this, the way we use all of these definitions and knowledge is to be able to determine the stresses, especially effective stresses. Actually, all of them matter. You have to be able to determine these stresses anywhere in your soil layers at any depth in order to tackle a soil mechanics problem. So next we are going to talk a little bit about doing that. So I will make a couple of very quick examples. So here is one. So let's say I have my I have my soils like this, and I have water table out here like this. So let me see if this pen is better. No, this is slightly better. So here is my water level, and here I have some soil where up here my unit weight is, let's say 16. Down here the saturated unit weight is 19. And basically the here is the depth scale, depth in meters, so to, let's say 5. So let's say this is the end of our problem. Actually, it doesn't have to be an actual end of layer. It can simply be the depth up to which I want to examine this. So actually you can even consider it like this. So the question here is going to be, calculate everything at all depths. So calculate the vertical total stress, effective stress, and pore pressure at every depth. So let's start with total vertical stress. And we can do that. The best way to do that is as a distribution over depth. So yeah, for a specific problem, you can end up needing the stress values for only a single depth. But most of the time, for most engineering problems, it's going to be much easier to visualize things and follow what is going on if you consider things in terms of a distribution. So at the very surface, there's nothing above that. So the weight is 0. Weight above is 0. So the total stress acting on the surface is 0. Then as I go down, for every meter depth, I'm adding a unit weight of I'm adding a weight of 16 kilonewtons. So per area, that would make 16 kilopascals. So in 2 meters, I'm going to get 2 times 16, 32 kPa. And then beyond that, between 2 and 5 meters, at every meter, I'm getting 19 kilopascals added to the question. So 32 plus 3 times 19. What's that? 57, 89. So it is still just like fluid pressures, but Instead, this time you have two immiscible fluids that have different densities. So imagine you had water and oil on top of each other, and then this would still be how pressure in that fluid would be distributed. So next, let's consider pore water pressures. Everything will be in kPa, all the stresses, because all of them are stresses. So up here, where the soil is dry, your pore pressure is going to be zero. Remember, if it is just air, it is zero. And then below here, basically this little sign, this triangle, upside down triangle with its reflection, it always tells you at this level water pressure is zero. So here it is zero as well. And then the rest is hydrostatic. Therefore, 3 times gamma water. In this chapter, I'm going to be using 10 for gamma water for simplicity of calculations. So if you want to be more precise, you can go ahead and use 9.8. By the way, a little side note, using something like 9.81 or 9.807 is going to be more precise, but not more accurate, because here in Ankara, due to our latitude as well as our elevation from sea level, actually the gravitational acceleration is much closer to 9.800 compared to 9.807. Just an additional little trivia. So finally, let's look at the vertical effective stress in kilopascals. So this one is always going to be total stress minus pore pressure, as we said. So here it goes. Here it is 32 minus 0, that's 32. And then the slope changes because up here it was going at a slope of dry unit weight or bulk unit weight. Here its slope is the submerged unit weight. Why? Because I'm subtracting from saturated unit weight sloped line, I'm subtracting a line with a slope of gamma water. So the result is a line with submerged unit weight. You can either think of it that way, so that would be either 32 plus 3 times 19 minus 10, or you could also think of it as Terzaghi's effective stress principle, which I really recommend. It is much easier to think that way. And either of them are going to make the value 59. So this is basically what we are going to be doing in this chapter, but there are, right now it looks like very straightforward, but there are many other possible complications I could add. So let's add a few more of them. Now, another example is, what if I have this? Let's say I have some sort of water body, let's say it's a lake, and this is 2-meter deep lake. And then let's do our calculations down to, again, 3 meters. So actually I'm giving the same geometry, but this time I'm just switching such that you have just water here and soil here. And let's use the same gamma saturated. So let's do the same exercise here. Okay, so again, at the surface, it is going to be 0. How much will it be in the water? Now remember, this is the total stress. And its definition, we defined it as, or we summarized it as, weight of everything above. So as you go deeper in the water, water's weight applies stress. Therefore, what you get is here 2 times 10, 20. And then the slope increases down here, 20 plus 3 times 19 is 79. No, sorry, 77. Let's look at the pore pressures. This time, remember, this is my water surface, so it is 0 up here. So here it is 2 times 10, here it is 5 times 10, because we are looking at a hydrostatic case. And lastly, the vertical effective stress. Up here, there is none. Down here, effective stress principle says 20 minus 20. This is also 0. Why is that? Because up to this point, there are no grains. Remember the vertical effective stress. The effective stress is the stress carried by the grains. So in the lake body, there are no soil grains. So it just goes like this. There's nothing with grains up there. Then the rest is, so here it is 20 minus 20 is 0. And here it is 77 minus 50. Which is also 3 times 19 minus 10, both of which make 27. So basically, this is the idea. It's always, these stresses can always be calculated in such a way